All right. So we're in the middle of the derivative rules. Let me go ahead and open those up. It's a good thing to have open. And we've mostly just talked about the power rule and the exponential rule, and we've started to dig into some other ones today. And I extended that homework that was due on Wednesday to tonight. So I'm happy to start by talking about some questions if people have them, or yeah, let's start there. Do people have homework questions that they want to look at? General questions about things? Yeah.
I was confused on number 4 in the limit derivatives one. It was more like a table, I think.
Okay, let's pull that one up. Yeah, Face ID is not going to work right now. Just take them my thing. Okay. Does that work now? Okay. So this is getting at the conceptual idea of what a derivative is, right? So we know that if we have a function, that the derivative tells us the rate of change, or in this case, let's consider it the slope of the tangent line. And so what we learned was if the derivative is positive, that means the function is increasing. And if the derivative is negative at a point, let me put a point in there, at a specific point, then that means f is decreasing at that point. Right, it's the difference between having an increasing tangent line or a decreasing tangent line. Right, so just kind of looking at the graph that I drew there, if the function's going to be going up, the derivative is positive, and the function's going to be going down, the derivative is negative, is what I'm trying to say. So when we look at the picture, we can look at these values and think about when are the numbers going up and down, and that'll tell us something about the derivative. Right, so if I look at this table here, it starts at -12. Let me zoom in on that table. Starts at -12 and then gets bigger, right? -9 is bigger than -12, -6 is bigger than -9, etc. So these values are all increasing. And so that should tell us that the derivative is positive here. But then it goes from -3 and it goes the other way, right? -4, -8, this piece right here would be decreasing. And so the derivative is going to be negative there. And I think that's what the question is asking about. I actually forgot to look at the question, but if I recall, it's a question about when the function is, when the positive, yeah, so when is the derivative positive, when is the derivative negative? And based on that, you can kind of think about, once you actually estimate that. So let me see if there's questions about, I basically just answered B and C. Are there questions? Is that okay? That makes sense? Pull the chat up here. I don't know if I'll catch questions online here, so just holler at me. Oh, and then, yeah, so we know how to do this too then, right? So if we want to approximate at 2, which is this point, right? We want to do the average rate of change a little bit before 2 and a little bit after 2. Let me see, did you get that one? Not yet. So for this piece, we would want to do 1/2. Right, this is the formula for approximating the rate of change. I know this is particularly confusing because we're talking about like all in the same kind of week here, we're talking about approximating the average rate or the instantaneous rate of change. We're talking about doing it with the limit definition. And then we're talking about doing it with rules, right? And so it's like 3 different versions of the exact same thing. One's an approximation, one is the exact definition, and the other ones are kind of like shortcuts is the way to think about them. Okay, that's about that. Let me send this over to, oh, where is it? Why isn't it here? That's unfortunate. There we go. I will go ahead and, if I can find that one, I'll put it in a folder. And we're frozen. Anyway, I'll try to have to do this one later. I don't know why this is always giving me so much trouble. Can't I just just did that? If I do that. All right, I'm gonna stop wasting time. Other homework questions? I'll try to get that one into the homework folder after class. Other things you want to talk about?
For the power exponent rules, like 4 and 11, so I don't know. Those are the ones I couldn't figure out.
Let's see, so 4 looks like that, 11.
I have a one down, but
Yeah, so they're both similar problems, I would say. We can just look at one of them, I would say then. Oh, I just do this first, is that helpful? So annoying, so annoying. So we did look at these last time. How'd you start this one?
so first I found the derivatives
Yep, what'd you get?
of 4. Well, the answer is 4, but for 1, not the
All right, so it's a good, we want to be writing this stuff down. I think that's usually a good idea. Otherwise, you probably just did it yesterday and you don't remember it, right? The whole point is to learn from this stuff. So that's the derivative. And then when we want to find the slope, you just plug the number that you're interested in. And we want the number 5. And so we're just going to plug in -5. And so the slope is -6 over -5 squared, which is what you ended up with. Right? So that's how you got that in the first one. Right, and so that goes into both those 2 spots. See that? We got 2 answers. They're the same answer because one's getting you to plug it into the derivative, and the second one's like, oh yeah, by the way, that's the slope of the tangent line. How do we do the third part? So the third part is just finding b in the equation y equals mx plus b. Any thoughts about that? I did one like that last class. So does anyone have those notes? Or John, do you have those notes? That's why I went over it last class.
So that's specific problem. That's not.
Well, no, just in general. When you want to find the b and y equals mx plus b, it's the same process every time. So I think I did it for a different problem, but the idea is that you're able to look at what we did and then translate it to a different problem. So any thoughts about that? Anyone? Gregory, what do you do there?
So you pointed the X and Y into the slope intercept equation and the slope as well. And then you find-
Okay, I'm gonna do that.
Yeah.
Thank you.
So I'll just write it down just in case someone's confused about that. You plug the point in that you're given. We just found the slope. And the X value was -5. And then you want to solve for B. And yeah, I did do one of those. So I would just, the reason I mentioned that is just so you can look at that one. Oh, guide you. Other things about this one? Wish I could figure out how to save this a little bit easier. What if I did this? I'm just going to save it there for now. So what you guys want to look up? Let's see how we're doing on time here. Spend a little more time on the problem if you guys are interested. You guys doing okay on this? Or just kind of shoot through real quick. Most people have finished most of these. Looks like people are either doing it or not. So that's good. All right. I'm going to start notes unless there's another question. So let's see here. Where were we specifically? So we looked at, right, we looked at the power rule and the exponential rule. Those are what was in the homework that is now due tonight. On this particular page, we're going to look at some sine and cosine rules, so some trig rules. We'll do natural log, and then we'll get into some other ones. So let's start with the sort of the easy ones, quote unquote. So back in the derivative rules, we're going to look at these three, right? Sine, cosine, and tangent. And sine and cosine are kind of interesting because when you take the derivative of one, it becomes the other one, right? So you can see that when you do the derivative of sine, it just becomes cosine. That's like the easiest, one of the easiest derivatives you should know. Sine just becomes cosine. Cosine does the same thing, but it's got a negative sign with it, right? See that? So that's the thing that you got to kind of be careful about. Sine changes right into cosine when you take the derivative, but cosine changes into minus sine. And then tangent becomes secant squared, also not too bad. So we're just going to look at this next one, and it's really pretty straightforward, I think, when you kind of think about those three things. And so if this is our f, then f prime is very simply 2 cosine x, right? Sine changes into cosine, no big deal. Cosine becomes minus sine, so it's going to be, maybe I'll write out the details. It's like plus 4 times minus sine. And then tangent turns into secant squared, so just minus 8 secant squared. And so the plus in between the cosine and the sine becomes a minus is what I was trying to allude to here. Sine and cosine are ones that kind of come up a decent amount. Tangent, we don't see particularly in our class, but it's one just to know, just to have an idea of moving forward. Yeah. Okay. Big deal. So sine turning into cosine and vice versa implies that the rate of change of sine at any point is equivalent to the value at cosine, which is kind of interesting, and vice versa. Right, so not only do they have their own function, but their function values describe the rate of change of the other one. It's kind of an interesting relationship. Natural log is another one that's not too terrible. Let's see here. So let me delete some of those things. Natural log, when you take the derivative of natural log, it just becomes 1 over x. So natural log of x, you got the x inside there. You just drop the natural log and do 1 over that. It's kind of an interesting one that has some interesting applications in the chain rule. So when we look at this one in the context of the chain rule, which we'll probably get to next week, some interesting things happen. In this particular one, though, we're just doing kind of a simple application here. And so if this is the one we're looking at, this becomes 1 over x, right? And the 9 is just a constant, and so that just becomes 0.
So I thought the 14 became 0 as well as part of the natural log.
So it's multiplying the natural log, right? And so when we're thinking about the derivative rules, that's this kind of situation, right? When you have a constant in front of a function and you take the derivative, the constant just comes along for the ride, right? And then you just kind of take the derivative of the thing with the x in it. See that? So yeah, the reason that the 9 goes away, so let's just look at that again, right? The reason that the 9 becomes a 0 is because there's a plus there, right? And so it's like its own thing. And so that becomes a 0 because when you take the derivative of a constant, we get 0. That we have that rule. But the 14 is multiplying, and so it's the constant multiple rule. The other good thought there. Other clarificational things? Is that okay? And so if we wanted, we could just write this a little bit simpler. Not a big deal, but this is also written as 14 over x. Right? No problem. Either one of those is fine. Okay. Just kind of leave it there. There are a couple other trig rules in here. If you just kind of notice, sometimes I write them down. Sometimes I do another example. Like there's secant and cosecant, for example, here. These kind of have funky rules, the ones I'm highlighting. They honestly just don't come up a whole lot, and you have the rules if you ever need them, and so I'm going to kind of skip on that. Okay. What we really want to do, what I'd like to do today is move into these more complicated ones, these product rules, right? We got the quotient rule. These are the ones that are starting to get into real functions that we might actually see in practice. So I just want to stop real quick. Are there questions about either of these or anything else before we keep going? Just want to make sure everyone's with me before we leave anyone behind or anything. Okay. Oh, wow. Okay. So the product rule, let's go back to the derivative rules. So we're starting to get into these ones right here. Product rule, quotient rule, chain rule. And these rules oftentimes use the ones above it. And so the product rule tells us what to do when things are being multiplied. Right, let me just go ahead and be clear about how each one of these apply. Right, the product rule is for multiplication. Right, the word product means multiply. The quotient rule is for things being divided. When you can see that's the form there. And the chain rule, that's kind of the funky one. That's the hardest one usually. That's for composite functions. Notice how in this chain rule example, there's a G inside the F. And we've been looking at that notation a decent amount already with like F of X plus H, that's like that kind of thing. And I harp on that a lot in pre-calc too. So if you had me last semester, that might look familiar too. Okay, so these are the kind of things that we're going to walk through. My guess is today we'll get through at least product rule, possibly quotient rule. We'll see how it goes. Questions? Need to check this message. All right. All right, let's do an example. So notice how all the ones under the product rule situation, you have two things being multiplied. So let me throw in some multiplication signs, right? So I just throw a red dot in between those two things because it's like one thing on the left times one thing on the right, right? The thing in the middle here, it's cosine times e to the x. I'm just trying to write in some multiplication signs. And then in the third one, we've got natural log times y squared, right? So we're multiplying two functions in each one of those cases. And so it's very much an application of the product rule. And so when we're looking, let me zoom in on this one. It's like, this is our f function, and we're multiplying it by this g function. And when we think about it like that, we want to use the product rule. Nope, that's not product. With those two things as our f and our g. And so I'm going to try to do at least the first one very, very carefully. I'll write out all the details and then maybe not write as many details moving forward. So if we wanted to do this one, we want to use the product rule. It's going to be this. So let's just review what the product rule says, right? It says when you want to take the derivative of two things being multiplied, you look at the first one and notice how you take the derivative of it right here, but not here. Right, so we've got the derivative on the first one, but not the second one. And then with g, we don't take the derivative and we do take the derivative, right? So sometimes you write this, or I'll refer to this as f prime g plus f g prime, right? The derivative of f times not doing anything to g plus not doing anything to f times the derivative of g. That's what that says right there. And so I'm going to write that out. I'm going to do the details of that. Let me know if this looks okay. So this becomes, we're going to do the derivative of the first function, leave the second function alone, plus leave the first function alone times the derivative of the second function. And I don't want to keep clicking back and forth. It'd be a good idea if you had those rules out so you can kind of refer to it. But you see how this is like, right, this is my f prime g, f g prime. What do you think? How's that look? Can I clarify something? We haven't done it yet, right? I'm just kind of setting it up, right? So when I write d over dy, that means I'm about to take the derivative, right? So like in this spot right here, we got to take the derivative, and then right here, we need to take the derivative. And so those require other rules, right? So we're kind of building on our rules. What rule are both of those things? They're both polynomials. And so what do we do on polynomials? What rule is that? It's the one that's in the homework for this week, the easy one. Yeah, these ones are just power rules. Right, you just have stuff raised to powers. And technically the constant rule too, right? There's some constants in there, like the 8's gonna go away. But mainly it's a power rule thing, right? And then so then we just do those power rules, and that's the answer. So let me do those power rules. Do we want to see the details of those power rules still? How many? I'll just do the details just in case people are still confused by that. So we bring down the power, multiply, subtract 1 off the power, right? So it ends up being 2 times 3 to the y to the 3 minus 1, and then 6 times 1 times y to the 1 minus 1. This might be the last time I do the details on the power rule. So let me know if you want to hear about that. Right, and then that other power rule, bring down the 1, subtract 1 off the power, and then the 8 just goes away. And so this will be our answer then, right? We'll get 6y squared minus 6 Thoughts on that one? Power rule? What do you think?
Would simplify it further?
Yeah, thank you for that question. So the question for people remote, do we want to simplify that at all? We could FOIL that out if you really wanted to. That's not the point of this problem, right? The point of the problem is we're doing calculus. Do you understand the rules? Do you understand the power rule? I would prefer you leave it like that, honestly, because it's just going to waste your time. If you multiply it out, that means I need to multiply it out to check it. That's not the point. So usually on a test and things like that, I will put in bold words, do not simplify. That's not the point of what we're trying to do here. John?
-6y in the third parenthesis.
Yeah, sorry, I left out the y. Thank you. Does everyone see that? There should be a y right here. I left out this y. I was just trying to copy down the thing on top of it. Yeah, so I just left that y off. So, okay, and then like on this one, sometimes you have a question about this, right? When you do y to the 0, that's just 1. And so it's like 18 times 1, so it just stays 18, right? In other words, when you take the derivative of just a variable, it just goes away. It becomes the number 1. Other thoughts, other questions, clarifying things? Thank you for that. Keep it coming. Anything in the chat? Nope. Yeah, so again, don't simplify it. That's not the point here. We're just trying to get down to here. You know, if this is part of a problem and then we wanted to use the derivative, like sometimes you want to find the max or something like that, then we might want to do some more algebra and things like that. But if we're just taking the derivative, the goal here is just to show me you know the derivative rules. Just leave it like that.
My paper, I just got the last one.
On a test, I would be okay if you felt like you could just write the last one down. I'm somewhat hesitant to say that because if it's like way off, I can't give you partial credit is sort of what I'm thinking. So if you feel very, very confident and you're in person and I know you're not cheating and all that, then I'm okay if you just kind of jump to the answer, especially on sort of a more simple one like this, I would call. But just know it's hard to give partial credit for wrong answers when it's just the wrong answer. Okay, I'm probably going to leave that middle one for you. It actually doesn't really matter. I'll do the next one and then I'll ask you to try the last one there. So it's another product rule, right? And we have, this is our F, this is our G. And these are now kind of they're not power rules, but we have rules for these ones. We just learned the cosine one. And e to the x is one we learned last time, but let me just remind you what that one is. E to the x just stays the same. Remember that? It's kind of funky. This is the e to the x rule. When you take the derivative of e to the x, it just stays e to the x. It's the best derivative rule out there. And so if we were going to do this one, we're going to do f prime g plus f g prime, right? So the derivative is going to be, I don't want to write the details, I've got room. So we're going to do the derivative of cosine, that's f prime. Leave g alone, leave the f alone, do the derivative of the g. Oops, that shouldn't be a plus though, that should be a multiplication. And e to the x just stays the same, so that like that right-hand half, the second half of that is just literally just a copy of the original function. But cosine, we just learned, changed to minus sign. So this is a not too bad one. That would be it. F prime g plus fg prime. Look all right? Questions about how to follow that rule? You know, a lot of these rules, I know I've said this, but a lot of the rules are just understanding what the rule is telling you to do and then identifying the parts in the problem you're working with, right? Like where's the F and the G? What do I do with those in the rule, right? That's what most of these rules are about. If there aren't questions, I was gonna ask you to give this one a go. No questions? All right, try that one. So there's very clearly two things being multiplied here again. And so you just do the product rule one more time. And again, we've just learned both these rules. We learned ln becomes 1 over y. Y squared is going to be a power rule. While you're working on that, I'm just going to kind of slowly write the answer down. I'll do the details again. What do you do with that negative sign in front of the ln? Does that like mean anything? Sometimes people get. Yeah, it's just like a -1 coefficient kind of thing. Right, so you want to think about minus lny as being like -1 times lny. So it just stays out in front. Doesn't really change anything. It's a constant coefficient. All right, so ln becomes 1 over y. We just learned that one. And the 2y is a power rule, right? So this just becomes, excuse me, minus 1 over y times y squared plus, or really it's a minus because there's a minus sign there. So I'm going to change it into a minus. And we could simplify that, but I'm just not going to. It's not the point. Right? In other words, on the right here, sometimes people get a little frustrated by this. You could write this as y squared over y, which is just minus y. That's fine if you want to simplify that. I'm just trying to avoid these unnecessary extra steps. I clarify anything about the power rule? Is that right? As is always the case in math, we're just building on this stuff, but it's particularly important with these rules, right? Because we have these kind of basic rules like the power rule and the sine and the cosine, the exponential, and then these are going to be inside more complicated rules. And sometimes you have complicated rules inside of complicated rules with minor rules inside of them. So I'm just trying to emphasize, like, we really want to be keeping up, or else it's just going to get really confusing. All right, is that okay? The quotient rule is next, and it's worse. It's a little bit worse in a good way. I don't know, is that possible? So the quotient rule tells us what to do when we have fractions. We have not fractions, but rational functions, not technically rational functions. When we have two functions that are being divided, I should have just stuck with that. Right, we've got two functions being divided, like the next couple on the page. Here's how you take the derivative. And so it's really ugly looking, right? And notice how the numerator actually looks kind of like the product rule, where you're like doing the derivative of one, not doing it on the other one, and then the opposite, except there's a minus between them. Oops. So this is something people always forget. They sort of think like, oh, the numerator is the same as the power rule. Notice how there's a minus here and there's a plus here. So you've got to have the minus sign in the right place. That's kind of an important difference. And then the other main difference, which is hopefully staring you in the face, is that there's a denominator, obviously, which is just taking the denominator in the original and squaring it. So you don't like do anything to it, you just square whatever was down there. It's a really funky kind of rule. But fractions are complicated, and so hopefully it's not too surprising that when you take the derivative of a fraction, it's kind of a pain. So anyway, let's just keep that in mind. So keep that out. I'll maybe flip back over there, but let's look at this one. And we want to use the quotient rule. So here, we're going to use the quotient rule. And again, we want to identify in the rule, what's the f and the g? And so we're going to use the quotient rule with f being the numerator, so that entire top. And g is just the entire bottom. And so yeah, the numerator is itself the sum of two things. But the point is, when we look at the rule, f is the entire numerator, right? Whatever's in the top, we just say it's f. And then we just use the formula, right? F prime g minus f g prime all over g squared. Sometimes it's not too bad. Sometimes it's really annoying. We're not going to simplify it. That's not the point. So let's go ahead and write this one down. I'll probably just do this one and ask you to try the next one. So the derivative should have room to write the details. We're going to do f prime g. So that's going to be the derivative of the top times the bottom minus, don't do anything to the top, and then take the derivative of the bottom. All over the bottom squared. I've got my f prime g, f g prime. I'll highlight the minus sign. And then on the bottom, I've got my g squared. We got to take the derivatives, right? We got to do the f prime, we got to do the g prime. We're not going to simplify things. And we haven't seen secant yet, so we'll switch back over there. But does that look okay? Just kind of referencing the formula. So secant's one of those funky ones. Secant, right here, you can see it becomes secant tangent. So you kind of like copy it over and then also multiply by tangent. So when we do that in the numerator, that's what will happen. So let's go ahead and do it. And then we get a power rule over on the right one, right? The x cubed is going to be a nice power rule. So there's just a little bit of work to do. Oh, and the 2x squared is also a power rule. So I'm not going to write down all that stuff there, but hopefully that makes sense. So secant becomes secant tangent. That's kind of sloppy. Let me try to make that a little better. And then 2x squared is a power rule, so that just becomes 4x. Hopefully that's okay. Let me know if that's not. Second part stays the same. And then the first part stays the same. And then the power rule on x cubed is just 3x squared. We might as well square the bottom out. So when you raise a power to a power, you multiply the powers. Not necessary that you do that, but easy enough to do. What do you think? Can I clarify something? I haven't had any questions so far. I don't know if it's just things are okay or what.
Pretty confident with this.
All right, that feels good. Sounds good. It's easier than the limit definition, right? That's for sure. We don't have to do any limits. Although the quiz today is going to be some limits, but maybe after that we'll kind of stop doing limits for a little bit. A couple of head shakes. Believe me, there's actually a lot more complicated things that we don't do. So that whole epsilon delta thing, if you remember that, there's like there's varying degrees of theory, right? There's like the rules that we're doing right now, which is like no theory. It's like, here's just follow these rules. You take the theory a little bit further, it's the limit definition, which is tricky, but it's still just algebra. The epsilon delta thing that I just did that one day, that's like the ultimate level of theory, and we're not even touching that stuff. So anyway, just trying to say it can get more complicated. Is that okay? Can I answer some questions? Let me pose this question to you. In the next section, what we're going to start doing is taking derivatives like this and setting them equal to 0 and solving, because that's how we find maxes and mins and things like that. So if we had a fraction and we wanted to set that equal to 0 and solve it, how do you do that? Just kind of thinking back to solving fraction equations, or maybe the other question is, how do you make a fraction 0? Like, when is a fraction 0? Is the top 0? Is the bottom 0? Are they both 0? Not super important right now, just wondering if anyone has a thought about that.
When either like y or x is 0. Right?
So the thing I'm trying to get at, I guess, is, and I'm not being super clear, is if you want a fraction to be 0, that means the top has to be 0. Right? The only way a fraction is 0 is when the numerator is 0. It has nothing to do with the bottom, in other words. And so just kind of looking forward, when we end up with these complicated fraction ones and we want them to be 0, we just ignore the bottom and we just set the top equal to 0. Anyway, we're going to talk more about that, but it just popped into my head as what's coming next, so I thought I'd just mention that. Okay, feel okay trying this one, next one? So give this next one a go. Again, I'm going to kind of slowly write some things down if you need some more pointers with it, but it's a really good idea just to give it a try when you're about to see the answer and all that kind of stuff, right? Just, it's a really important part of learning. So we want to identify the F and the G. I'm going to just start by doing that and kind of slowly write it down. Right? So the F, the numerator, G is the denominator. We're just going to use the quotient rule. I don't have a ton of room here, so maybe I will just write it down here. Just going to write the details. 2t squared. Oops. This is definitely one where you just don't multiply the bottom out.
I was just doing that and I was like, yeah, this is a mistake.
Yeah, exactly. Just that's not the point here. Especially like if we were going to use this problem, like I just said, the denominator has nothing to do with solving equations, and it's just like, just leave it as it. Just leave it as that thing squared. Okay, so I had to shrink down my left-hand side, so it's kind of hard to read, but I'm trying to do f prime g minus fg prime, right? F is the top, g is the bottom, and it ends up looking like that. I think that looks fine. Just checking my work, seems okay. Thoughts about the quotient rule at all? On time here. I'm just going to introduce the chain rule. The chain rule is the one that usually people have the trickiest time with, which is why there's a whole page about it. No one here is writing, so I'm going to start going on to that. So again, the chain rule is what we do when there's something plugged into something else. Right, so maybe let me just do a couple examples of composition functions. So if we had like f is x squared and g was, I don't know, 3x plus 7 or something like that. If we plugged g into f, it would be that, right? That's the kind of thing we've been practicing. Like you take out the f or the x in the f function, put in g. And so this is how we recognize something as being composition. Or something like, let's say we had, maybe, let me color code this one. Let's say we had f was cosine of x, and maybe g was e to the 2x squared. If we did f of g, that's me writing down the f function and putting the g thing inside of it. And so these are the types of functions. And if you look, I'll flip back to the other page in a second, but if you look at that page, there are these kind of things. There's like, hey, we have an x squared, but there's something inside of it. Or hey, we have a cosine, but there's something else in there. And this rule tells us how to handle those things. Right? These are particularly tricky because you have two different things and they're not just next to each other or on top of each other, they're like inside of each other. So it's particularly tricky. Can I clarify something about just a couple examples I did there? Do people kind of see how that worked? Because the first step in these things is recognizing what's inside what. And so I'm trying to like give you some intuition there. So notice how, let me just remind myself. Yeah, we're gonna really fill this page up. I should have given myself some more room on this next page, probably. We'll be okay. Okay, but notice what happens. When you recognize what's inside what, and then when you do the derivative, you do the derivative of the outside function with the inside one still there. That's what this piece says right here. And then you multiply it times the derivative of the inside piece. That's what this is telling us to do. So I'm going to rewrite that down at the top of the next page. So here's the chain rule. I'm just going to write the chain rule down right at the top here. If we want to differentiate a composition function, we do f prime of g of x times g prime of x. Just kind of, this is going to be good to reference. And so just look at the three there on the page, right? It's like the first one is an x cubed, and there's another polynomial inside it. Right? This one here is an e to the x with the 2x squared in it. This one is a natural log with a 1/2 t inside of it, right? So we're trying to identify what's inside what. I'm just going to do one example, and we'll pick up with this next week. I'm going to start with the one on the top left. So when I look at this h of y example, I'm trying to think about what are the two pieces? What's the f and what's the g? And so I'm thinking, well, it looks like something's being cubed, right? There's like a cube on the outside. That's what's giving me that intuition. And then I'm thinking, well, what's inside of it is a 2y cubed plus 16y.
So this is like the opposite of what we were doing on class. Now we're trying to go backwards.
In some sense, yeah. So previously you're talking about like this kind of thing, right? Like taking out the x and putting in the x plus h. So yeah, that was taking things out and plugging things in. Now we're looking at something where something's already been plugged in, and we're trying to think about what was plugged into what. So yeah, it's going in the opposite direction of that concept. All right, so, and the reason I arrived at that, because this one's on the outside, and this one's on the inside. Is that okay? Definitely gonna need more room here. I write much smaller, I think, when I'm not on my iPad, it turns out. At least here I can shrink things, I guess. Let me just shrink this a little bit. So is that okay identifying those two things? Because now we want to take their derivatives, right? This thing's telling us we need their derivatives. So I'm going to do their derivatives. And so G prime is an easy one. They're both easy, actually, because they're both power rules. All right, so F prime is just 3y squared. And G prime is 6y squared plus 16. And so we have one of the pieces we want. G of y is one of the things we want in the formula, and we now have that one. but we don't have the other piece, right? The other piece is not f prime of y, it's f prime with g plugged into it. So we still need to figure out this piece. And it uses this, but it's not that. We need to plug g in there.
Would be 3 parentheses, 12 parentheses squared.
Yep. And then the g is going inside there, right? And so these are the two things we want to use. Right, those are the two pieces of the formula. Yeah, I wish I moved this a little bit. I'm gonna slide things around, and I apologize, but I wish I did this. But it didn't really work, did it? Let's see. So I just want to do that so I could write the answer down right below it. So the final answer then, h prime is going to be f prime of g of y times g prime. And we have those two pieces, so it's going to be so the reason it gets complicated again is because you have something inside the other thing, right? So it's kind of like you ignore what's inside it, take the derivative of the outside piece, but then put the other one back in, right? You like simplify it. In other words, doing this kind of thing, ignoring what's inside it and then taking the derivative of that is easier than trying to think about what the derivative of it is with it inside. So you kind of like ignore what's inside of it, take the derivative, but then remind yourself, oh yeah, but there was something in there. That's sort of like the F part of it. And then you need to account for the inside part somehow. And so accounting for the inside part is where the second part comes in, where you just multiply by the derivative of that inside piece. It's definitely the trickiest rule. And you can imagine how it eventually involves other rules, right? So it snowballs a little bit and it just keeps getting complicated. But we're just following the rules. We're trying to follow those rules. And if we can do that, we're going to be okay. There's lots of other examples on this page, right? There's other examples in the homework. We're going to spend at least the next couple class periods on this kind of idea. Thank you.
Two y cubed. You have 2y cubed.
What happened?
Squared.
2y cubed.
Plus x.
Yes, I did switch those. Sorry about that. Does everyone see that? I just changed what this was. Okay, I want to move on so we can have enough time for the quiz. We're going to spend lots of time on this. This is in the homework for next week. I'm okay. Well, anyway, it's in the homework next week. Come with questions about the homework too. And we'll keep looking at this stuff next week as well. I'm going to start just passing this quiz out just so you have enough time. There's only 2 questions, but they're limit questions, so I don't know if that's Okay, Sean, you there?
Yes.
Can you turn your camera on, please? Same thing over and over again. You just put it right over there. Soda pile. Thank you. Have a good weekend. Yeah.
I'm completely stumped on how to continue.
Any ideas? How do we, let's just ask class, how's everyone doing on the first one? So you plug it in, and then what technique should you be using? Gregor? Yeah, so it should be the conjugate over conjugate one, exactly. Yeah, anytime you got square roots in there, you should be doing that one. I think one of the first examples we did in the notes was kind of similar to this one, if I'm not mistaken, just thinking from memory, but. Then maybe I'll just also just give you the hint in case you need it. In the second one, B is 1, right? I didn't, I guess, explicitly say that, but B is 1 in the second one. Right there, thank you. H is going with 0. Where does it turn it on? So if it was an H here. So this H. Then it becomes 0. Thank you. Have a good night.